So this one is a little bit odd, especially it seems kind of contrary to what we talked about before, but we're going to roll with it, we're going to talk about it, and it should be fine. So in this one we're saying a rectangular circuit that is placed on a horizontal table is represented in the top view figure above. The circuit consists of a battery with potential difference delta V naught, an open switch, a resistor of resistance R, and a capacitor of capacitance C that are all connected in series. The switch is closed at t equals 0. What is the direction of the magnetic force exerted on the wire on the left of the circuit? So we want to know on this one, due to the wire on the right side of the circuit after the switch is closed and current flows through the circuit. So we're looking immediately after it closes. So based on our knowledge of capacitors, immediately after it closes, we still have current going through here. It pretends like it's just like a wire. So we say, okay, current's still flowing, so that's good. And current's going to flow. This is our negative end. This is our positive end. Electrons are going to be scared away from this negative end is how we're going to talk about it. So we're saying current's going down in this direction. And then over here, current is going in this direction. So then we have to use our right-hand rules to figure this out. So if we use our second right-hand rule, around this wire, we have our thumb be the current, and then our fingers be the magnetic field. To the left of it, our magnetic field is coming out of the page. And to the right of it, our magnetic field is into the page, but we don't care about that as much. So to the left, we have all out of the page, which means over here, we have a magnetic field that is out of the page, right where we have that current. And when we have current going through a magnetic field, there's a force applied on that current. So now we can use our first right-hand rule. We can say, okay, our index finger is in the direction of the current. Our middle finger is our magnetic field, so that is pointing up. And if you do that, your thumb automatically goes to the left, which means that our force is to the left. So what's weird here is before we had that question with the loop of wire, and we said, okay, there's no force acting on this thing because an object can't exert a force on itself. So when we say that, we mean an object can't really exert like a net force on itself. So here we have kind of the right side is exerting a force on the left side, but the left side is also exerting a force on the right side. So they're going to kind of balance each other out. So we do have a force here. We also kind of have an opposite force there. So we don't really have to worry about the definitions of force in this case. We're asking more in particular, what is this wire doing to the left wire? So yeah, so we have to the left.